graph of the actual derivative, and we want to use that to graph the function. So there were different things that we had to think about, like we had to think about that chart is very useful, but we want to think about, what a positive derivative mean, what an increasing derivative mean, and things like that. For me, I do think it helps to divide the graph up into sections, especially when you first start these problems. So if I'm going from f prime to f, I know the first major thing we know is when the derivative is negative, the function is decreasing. And when the derivative is positive, the function is increasing. So I know that like at -7 is kind of a dividing point, -3 is a dividing point, 2 is a dividing point, and then 3 is also a dividing point. I also know that what the derivative is doing, so is it increasing or decreasing itself, affects the concavity of the function. So I also add some things there. So the derivative changes from increasing to decreasing at -5. Starting at like -1, it gets a little flat, so I'm gonna kind of treat that as a separate interval. And then it's increasing at the very end. Even though it does flatten out like a little bit, I'm just gonna treat that as all increasing. And then I use that to kind of figure out what my function f, again, the original function, looks like. Again, we don't know exactly where it's at, so we just care about the general shape. And I just think section by section, I think to myself, well, what is this function doing? So in this first section on the very far left-hand side, my derivative is negative, so I know that the function is decreasing. The derivative is increasing, so my function would be concave up. So I know I'm going to draw something that is decreasing and concave up. These next two sections, I see that the function is going to be increasing because the derivative is positive. The derivative is negative here, still negative, so I know that my function will be decreasing whenever the derivative is negative. And then once the derivative begins to be positive, the function is going to start increasing. Then I'm going to do the same thing for concavity. An increasing derivative means concave up. A decreasing derivative means concave down, concave down. This section's kind of interesting. Around 0, we see it's flat, so it has no concavity. So it is going to be a constant straight line with about a slope of -2. Then it switches back to be concave up, and then this is increasing. There's like a brief flat section there, but for the most part, it's going to be concave up. Again, the chart is useful to you until you kind of just memorize it of kind of what the derivative relationship is with the function. But then when I go to graph it, again, the y value doesn't matter. I just want to kind of pick a starting point and go with it. So I first have this first section needs to be decreasing and concave up. I see I'm going to be increasing and decreasing for a while, so I'm just going to start somewhere in the middle. So decreasing and concave up. Next section is increasing and concave up. Next section is increasing and concave down. Then we have decreasing and concave down. No concavity, but it does have a straight line slope of -2. I'll just estimate that. Let me estimate it a little bit better. -2 is probably steeper than that. Again, I really just want the basic shape. So we have the straight line here, decreasing and concave up. So again, be careful, even though the derivative is increasing, that just tells you your function is concave up. And then this last section is going to be increasing and concave up for the rest of the graph. So this green graph I drew is just an example of what f could look like. Again, we don't really know the exact y values because that information is not provided to us, but we can kind of use the derivative to figure out at least the general shape of that function. Any questions or how I kind of figured out stuff from there? Mitchell, your hand's up.
Yeah, so is this the one where you, from f prime to f, the y value doesn't matter?
Yes.
Okay.
So the last 2 days we've looked at sketching graphs. We went from f to f prime and f prime to f. Today what we're going to look at is justifications. And I'm going to spend a lot of time, like today is more just going to be like the idea of like how do we write a good justification. I'm not really going to get into a lot of the examples of justifications until Monday when I have some like classwork problems that we're going to work on. So before I kind of go over this, I am going to go over this slide. I did share it with you. It's actually more than a slide. It's like a full sheet of paper. But again, writing in math is very different from writing in any other class. So what I've done here is I have like the question of what it would look like, and then I have an example of just a flat out wrong answer. I have one that is correct but will be considered vague, and then I have one that's correct but is way too wordy, and that very last column is what you want your goal to be every time. No math person is impressed by how many words you can use in an explanation. Like just leave the adjectives and the descriptions for English class. A math person just wants, just tell me what it is and get your answer out as clearly and concisely as possible. So when I talk about what your answers should be when you justify your answers, we want to be clear, we want to be concise, and then obviously we also want to be correct. What do I mean by saying that I want you to be clear is I want you to avoid ambiguity. So I want you to go ahead when you are explaining your answers, you're going to eliminate certain words from your vocabulary. Like I don't want you to say it, like I don't know what it is, I want you to say what you mean. So say the derivative is, or the first derivative is. Don't say it, I want you to avoid it. In fact, if we're in person and taking pencil and paper tests, because I'm extra, I actually have a stamp. I'll hold it up, it's gonna be backward on the screen, but it's a stamp that's literally the word it with a line through it. And I will go to town with this normally if you start using justifications and you're like, it's positive, because I don't know what it is except for that creepy clown in that movie. So we're not gonna use it at all. You want to be clear, talk about the derivative, the first derivative, the second derivative. It's also good beyond it just to avoid other things as well. Like I would avoid saying things like the graph or the slope, because if you just say the graph, a reader, especially like an AP grader, may not know if you're talking about the graph of the derivative or the graph of the original function. So we're just going to make sure we're always clear about what we want to say. And then another issue that I find, especially for kids in AP calculus, you tend to be the good students. You like to be very thorough with your explanations. And sometimes when students tend to get thorough, they just get very, very wordy. Like if I'm reading your explanation and I get bored halfway through because there's too many words on it in it, that's probably not good. So you look at this column that says clear and not concise, like one of the answers I have is decreasing because the y value on the f prime graph is negative, so the line tangent to the graph of f has a negative slope. Like congrats for using a lot of words, but just don't be wordy. I want you to say exactly what you mean. And so if you're looking at this very last column, just look how nice and clear and concise and easy to grade those explanations are. So I do want us to worry about being clear and concise. So what I've done is I have created, before we do an actual example, I have this handout, which I haven't always used it, but I find it is helpful for a lot of students. So there's actual numbers that we're going to put in our answers, but I just want to talk about how we would prove whether a graph is a certain thing. So I have the justification, we have like the notes is what we're going to look at. And there are going to be two things that we're going to talk about when we're justifying. We're going to talk about like, am I justifying using my original function? Or am I justifying by using the derivative? So I'm going to talk about justifying using the original function now. And one thing about calculus also that I should mention, when you are justifying your answer, you want to use the given provided information. So if you're looking at f of x, your because better include f of x. If you're looking at f prime, then your because better include f prime. So how I have this, like I have a graph there, like we're not going to really use it for this example. But if I want to justify an answer based off of f, we know that we can interpret different things on f in regards to what f prime is. So if I ever ask you to say, hey, tell me where f prime is positive, you'll basically frame your answer as f prime of a is positive because, and you will say something like f is increasing at x is equal to a. No need to get all wordy and say things like, because the points are moving in an upward direction and has a positive slopes, therefore it's increasing. No, just say f is increasing, and that's how we know f prime is positive. Same thing if I say f prime is negative, we know f prime is negative if f is decreasing at the x value that we are looking at. If you're trying to justify where f prime is equal to 0, you're going to look for where f has a horizontal tangent line. And again, this is just another way of really writing down that chart. So we've already filled in the chart one time. This is just a way of writing out the chart in terms of like statements and justifications. If we're looking for where f prime of a is not defined, there are going to be different things that we can use. So this graph I had written it so it was something like f is discontinuous at x is equal to a, but that discontinuous you can replace with other things as well depending on what you know is going to keep the derivative from existing. For example, you might say it has a vertical asymptote there, or you might say that it has a vertical tangent there as well. But again, we're just taking that chart and kind of unwrapping it on the graph. These last few rows are kind of where I start seeing some things making a mistake. And the first common mistake, like I hate to guarantee that's going to happen, but it's going to happen because it always happens, is this statement where I say f prime is increasing. If I say f prime is increasing, what is that talking about in the graph? What is the function going to look like if I say f prime is increasing?
Is it that it's concave up?
That the graph is concave up. So I'm actually going to link two of these together. When I say f prime is increasing, this is the same thing as saying f double prime is positive. Those two statements are exactly identical and interchangeable. So if I ask you to find somewhere where f prime is increasing, you're going to look for where f is concave up. And we'll say at x is equal to a. So same thing for that one I linked it to. F double prime is positive means f prime is increasing because for the same reason, f is concave up at x is equal to a. And then likewise, we can link some other ones together. When I say f prime is decreasing, that's the same thing as saying that the function is concave down, or the same thing as saying the second derivative is negative. So we'll be looking for when f is concave down at x is equal to a, and I can repeat that f is concave down at x is equal to a. Notice if I am proving something with f prime, I'm talking about the graph of f. So I don't think there's any new information there, like it's just taking that chart and putting it more into words and how we form justifications. But is there any questions that I should clarify a little bit better on that side?
Yes.
Go ahead.
So something I've noticed is when talking about tangents, the abbreviation has a G at the end. If we put down tan, would that be confused with cosine, sine, tangent?
So the thing about abbreviations, like there's no official abbreviation for tangent. I just personally put the G on there so it's not confused with the tangent that goes with trig. But I will be able to figure out what you mean. If it was an AP exam, I'd probably recommend just writing out the word tangent, just so the AP graders can't give you a benefit of a doubt.
Okay. I wasn't sure. So
yeah, it's really just my abbreviation. So then on the other side of this, like I took the numbers off of this so we can just talk about how we would justify our answer. if I give you the graph of f prime, you want to justify your answer using f prime. So this is actually going to look very similar to what we just wrote down. In some ways, I want it to feel redundant because I want it to feel like, there are a lot of connections. There's a lot of things that you already know, and hopefully build some confidence when you start doing these justifications on your own. So if you're looking for where f of x is increasing, we're going to talk about the derivative now. So if you're proving that f of x is increasing, you will know something like f prime of a is positive or greater than 0. If you're looking at where f of x is decreasing, that is where the derivative at a is less than 0. Again, you can say is positive or is negative. I like the inequalities because, again, it kind of goes back to being very clear and concise. Notice this is where people sometimes like to get wordy, like they'll say something like, oh, f of x is increasing because the y values of the derivative are going up as you move from left to right, or something crazy like that. Again, the more distinct we can be, the shorter we can be, actually the better. Where does f of x have a horizontal tangent line? We know a horizontal tangent line is always going to occur when the derivative is just simply equal to 0. F of x is non-differentiable. That word non-differentiable, again, just means there is no derivative. So if you're proving where there is no derivative, you're just looking for where f prime is undefined at. And then we also can go back to these concavity ones where if students make a mistake, it's often when they're trying to justify some concavity. So different things you can do, we can say that f is concave up. We know f is concave up when f prime is increasing. We can also link this again to if I'm looking for where the second derivative is positive. So those two are also, again, linked together. F prime is increasing means function is concave up, which means the derivative is positive. And I can also link these two together. Concave down would mean where f prime is decreasing, and again, repeated f prime is decreasing. So I don't want you to I really just don't want to keep you forever today. I wanted you to be able to start your weekend early. So I just have one example with justifications. Tomorrow or Monday, we're going to work on this assignment together. And then Tuesday, we'll work on this assignment together. But today, I just wanted to finish up with a short one, just so you can kind of see how the justifications are worded. So this is a graph that we dealt with yesterday. This is f prime. So we are looking at f prime. So that means when I justify my answer, my because is going to be because f prime is something. So I'm going to use f prime to justify my answer. And also things I'll say, like if you ever see JYA, I use that abbreviation a lot. That's kind of also just a Mr. Brown abbreviation. That just means justify your answer. And again, justifying your answer, you want to be as clear and concise as possible. So looking at this, it says find a value for C for which the following statement is true. So I want you to find an x value where f of x, the original function, would be increasing and concave up. So there's different answers we can use here. Me personally, when I start these problems, it's often easier for me to do the justification first before I provide the answer. So I am looking for where this graph is, where my original function is increasing, and where my original function is concave up. So let's think about what our justification would be. I'm going to do the increasing part first. So I'm looking at f prime. If my function is increasing, what am I looking for in regards of f prime? What would f prime be if f is increasing?
Positive.
It would be positive. So I know that I'm going to have f prime, I'm going to leave it blank for the number there, and say greater than 0. You could have also written is positive. And then let's also justify the second part, concave up. So I'm going to go ahead and do the and. In regards to the first derivative, what would the first derivative be, or what would the first derivative be doing if your original function is concave up?
Increasing.
Increasing. So I'm gonna go ahead and fill in my justification. F prime is increasing at, and then we're gonna find the C value. So if I'm looking at this graph, I'm gonna look for a piece of the graph that is positive. So here's the positive derivative. I know my function would be increasing over those intervals, but I also want to look for the intervals where f prime is increasing. That's where it would be concave up at. These overlapping sections will be the ones where I can pull my answers from. So in this interval, I can see that f prime is both positive and increasing. Also on this side, f prime is both positive and increasing. So I'm just going to pick one of them so you can kind of see how the justifications work. And I'm going to choose this value right here, where x is equal to -8. And so one example for C is, hey, at the x value of -8, I know my original function is increasing and concave up because the derivative at -8 is greater than 0, and the graph is increasing on the derivative at -8. So I know that in the original function, it would be increasing and concave up. Now we actually drew this one yesterday. I'm about to pull it up so we can compare it. We drew this one. Here's what our graph looked like. At -8, it's down here. We can see that the graph is increasing there and concave up. So we can kind of see how our justification made connections to something that we already did. But that's really what I'm looking for when we're doing justifications. Like I want them to be clear, I want them to be concise, and obviously I also want them to be correct. So at this time I am going to go ahead, like I am done with class. So you can, I guess, have an early weekend or get started on any homework. Homework that you can do now. So if I'm going back to the calendar. So before I told you just do f to f prime, and then yesterday I added you can do f prime to f. Now I can finally add to that, you can basically just do all of that homework number 3. So the homeworks that are going to be on your quiz, again, the quiz is not until next Thursday, are basically going to be the topics on homeworks 1, 2, and 3. I do think of those, number 3 is probably the one that takes the most time, and it is probably the most challenging one. Next week, Monday and Tuesday, we're going to be reviewing during class time. Wednesdays do begin the asynchronous Wednesdays we have during phase 3. So it'll kind of be like a full day of office hours and then time for you to review on your own. And then we'll have our quiz on Thursday. For those of you who do plan to come in person, I've gotten the room set up so that things are spaced out as they need it to be. If you're just concerned about like the maximum number of students in at a time, if your day is Monday, there's a maximum of 4 students in my class. On Tuesday, it will be a maximum of 6. Thursday, a maximum of 6, and then Friday, there's not many kids with the end of the alphabet name here, so on Friday, there'll just be a maximum of 2 of y'all. So it will be we have plenty of room to be spaced out. But that being said, I do hope everyone has a good weekend. Feel free to hang out in the meeting if you had any questions or things that you wanted me to clarify. We'll kind of regroup and do more justifications on Monday. But with that being said, see y'all, have a good weekend, or hang out and ask any questions you have about content, homework, or phase 3. Mitchell, what's up?
Yeah, so will you be open on the Wednesday for virtual office hours before the quiz?
Yes, so it'll be office hours all day, like not just 2 to 3:30.
Oh, really?
For me at least, yeah, because there's no schedule on Wednesday, so.
What? Okay, when does that close? Does that close at like around 2? Will be open all day.
Where teachers are told to be available on Wednesdays from 8:20 to 3:30.
Okay, awesome.
So, yeah, it'll be completely open the whole day.
Thanks, Mr. Brown. Have a good weekend.
See you, Armani.
Bye, have a good weekend.
Bye, Mitchell.
Mr. Brown.
Yes, okay.
I'm having trouble signing in to think OneDrive on my Surface. Like, I know there's a specific place to go to for tech issues.